So this is part 2 of the elemental composition of pure substances. The other day I did the easier of the part of this section where we only had to do percent composition, or we only had to do empirical formula or molecular formula. Not that those things are easy, because chemistry is never really easy, but they are easier than these types of questions I'm going to introduce you to today. So we're still solving for empirical formula, but this is going to be from more complicated information. And so this first question is solving empirical formula from a combustion reaction. This type of question was on the FRQ for the 2025 AP Chem exam. And so it is a fair game to be a question that you could see on the end of the year exam. Let's start by talking about combustion reactions and review that. So a combustion reaction starts with some sort of organic compound that's oxidized and produces carbon dioxide and water. That organic compound is always going to be some kind of hydrocarbon, meaning it contains carbon and hydrogen, and it could also contain oxygen, but it doesn't have to. Plus, oxidation means it's being exposed to oxygen, so O2, and it always yields your H2O and carbon dioxide. And so in these types of problems, they're going to give you different pieces of information. And it's like a puzzle. You got to use that information to figure out the final empirical formula. So two of the pieces of information they almost always give you is the mass of carbon dioxide and the mass of water. When they give you those, you're going to have to figure out how many moles of carbon there are, how many moles of hydrogen there are, divide by that smallest number of moles. And then we still use those rules that we saw yesterday in the last lesson about how to round once you've divided through by your smallest number of moles. And then we write that final chemical formula for your hydrocarbon. Hydrocarbons are always written as C first, then H, and then if O exists, then we put O after that. So let's go ahead and do this problem. So this is an example multiple choice question from AP type questions. And this one is going to involve both carbon and oxygen, and then it also has nitrogen involved in this one. It says and some CO or some NO2. So it's a sample of a compound that contains only the elements C, H, and N is burned completely in O2 to produce 44.0 grams of CO2, 45.0 grams of H2O, and some NO2. A possible empirical formula for this compound is. So it doesn't even say it's an oxidation problem, but the fact that it says is burned completely in O2 is telling you it's a combustion reaction. And so that is your hint to how to solve it. So when you do this type of problem, again, our first steps are going to be to convert into my moles of C. And so let me get onto the pencil. So for this one, I'm going to start with my 44.0 grams of CO2. So I'm going to cancel with my grams of CO2 on the bottom. That number comes from the periodic table. It ends up being 44.01, the mass of 1 carbon, 2 oxygen. This is going to be equal to 1 mole of CO2. And if you just want to go ahead and do all the steps at the same time, you can just continue on. Because now that we have it into moles of CO2, we can convert it into moles of C, which is one of my steps for this type of problem. This is like in the very first section, the 1.1, when I taught you that you can convert between molecules and atoms using a chemical formula. We're doing the same thing here. So 1 mole of CO2 is equal to 1 mole of C, because in the chemical formula for CO2, there is an understood 1 carbon. So relative number of each ratio is also your relative number of moles. So then I'm going to mathematically calculate this. So I'm going to do 44 times 1 divided by 44.01 times 1 divided by 1. And when you do that, you end up with it, because I need 3 sig figs, it ends up being 1.00 mole of C. Now I'm going to do the same exact thing, but this time I'm going to do it with water. So I'm going to do 45.0 grams of H2O times. So again, I'm going to put grams of H2O down on the bottom. This is going to be 18.016. 2 hydrogens, 1 oxygen. Be sure that you're working these problems out and make sure that you understand where I'm getting these numbers, because you need to know A, how to figure this out on your own, and B, how to use your calculator. And I know that sounds so silly, but that is an issue that I have a lot, is people not knowing how to plug things into a calculator to get the right answer. They can set it up, but they can't get the right answer. And so then on top of this is going to be 1 mole of H2O. Again, I'm just going to keep doing my conversion because I've got to get to moles of hydrogen. So on the bottom, I'm cancel with 1 mole of H2O to 2 moles of H, because in this one I do have a subscript. So I'm going to do 45 divided by 18.016 times 2, rounded to 3 sig figs again, and it ends up being 1.00 mole of hold on, let me recalculate that one. That does not. That ends up being 5. That's what I get for trying to do math in my head. It doesn't ever go well. So it ends up being 5.00 moles of H. So then what I'm going to do is I'm going to divide through by my smallest number of moles, which is 1. So 1 divided by 1 gives me 1. 5 divided by 1 gives me 5. So I know that I have 1 carbon, and I know that I have 5 hydrogens. I can get that from doing my conversions. I don't know how many N's I'm going to have in this formula because it doesn't give me enough information. It just says and some NO2. But if we look over here, I have CH2, CH5, C2H5, and C3H3. Well, the only one that matches my information is letter B, the CH5N, because I end up with CH5, and then I just have to assume that since that's my only CH5, that the N was just a ratio of 1. So in some of these problems, they're going to give you all the information needed, and some of the problems, they'll only give you a little bit, and then you have to use the information you know to pick the correct answer choice. So on the next slide, it's a little bit more complicated, because this one says, what's the empirical formula? And it tells you that something contains CH and O if the combustion of isopropyl alcohol sample produces 0.561 grams of CO2 and 0.306 grams of H2O and 0.068 grams of O. So this problem originally was a lot more complicated, but we haven't seen AP asking questions to the complicated level that this question was asking you to do. In college level, you're going to do some of these problems that are a little bit more complicated. This one, I tried to simplify it down. So at this point, we already know our grams of oxygen by ourselves. We do not know our individual amounts for carbon and hydrogen. So let's start by doing our conversions. So I'm going to start with 0.561 grams of CO2. Again, on the last slide, we calculated it out. It's 44.01 grams of CO2 to 1 mole of CO2. And then we also saw that in 1 mole of CO2, there is only 1 mole of C. So then I'm going to calculate this out. So I'm going to do 0.561 divided by 44.01. I need 3 sig figs, so it ends up being 0.0127. Now, this is something that you're going to have to get really comfy with. Numbers in chemistry are never pretty, and they're usually really small. We deal with a lot of numbers that have leading zeros. After the decimal, we end up with a lot of numbers that have the numbers so small or so big it's in scientific notation. So you just need to get used to being comfortable with these numbers not always being pretty. Pure math is pretty, chemistry is not. So then my next one I'm going to do is my amount of water. So I have 0.306 grams of H2O. That one was 18.016 grams of H2O. to 1 mole H2O. 1 mole of H2O is equal to 2 moles of H. So then I'm going to do 0.306 divided by 18.016 times 2. And I end up with 0.0340 because the way that the sig figs make it round up. So 0.0340 mole hydrogen. And then I got to do something with this little oxygen. It's already given to you in that format. Like I said, I changed this question because I realized that AP does not ask it as complicated as they used to. And so I'm slowly changing some stuff over to represent the more likely type of questioning you're going to see on the AP exam. So then if it's just oxygen, I'm going to do 16.00 grams of O to 1 mole of O. And that comes out to 0.0043. Now, at this point, I divide through by which number is the smallest, and this is where it really comes in handy if you're super comfy with numbers, because this is the smallest number. If you would prefer to change these things into scientific notation, you're more than welcome to, but it is not necessary. So I'm going to divide by 0.0043. That gives me 1. So for this one, I'm going to do 0.0127 divided by 0.0043. And it gives me 2.95. Well, my rules for empirical formula, if it is 0.8 or 0.9, it rounds up. So 2.95 is going to round up to 3. And then on this one, 0.0340 divided by 0.0043 comes out to 7.9. Again, that's going to round up. So this is going to round up to 8. So my final formula, carbon is always listed first, is going to be C3H8O. So those are the combustion problems. And like I said, they're not really terribly difficult. It's a little time consuming. You just have to remember all the conversions you have to do. Sometimes it's only going to be carbon and hydrogen. Sometimes they might throw in another element. The other type of problem you're going to have is dealing with something called a hydrate. And a hydrate is just a compound that has extra water molecules that are part of its structure. They are chemically bonded to it. And so anhydrous means that the water has been driven off the hydrate. It makes it be a different compound. It makes them appear differently. We have a copper sulfate that is a hydrate, and whenever it is hydrated, it is a very dark blue powder. Once we drive off the water or make the water evaporate off, separate from that chemical compound, it becomes almost white. It's like a very, very pale blue. So they look different, which means a chemical change has occurred. And so it's just to get you comfy with the formulas that we're seeing here. Let's go through and name these hydrates and also review some rules for naming. So all of these are going to be transition metals. And so often when we have a transition metal, we have to include a Roman numeral in the name. So have CuCl2. This dot represents that it's chemically bonded to the CuCl2 to H2O. So CuCl2, Cu is going to be copper. It does need a Roman numeral, and I get that by working backwards. I know chlorine is a -1. If it is a -1 and there's 2 of them, overall I have a -2. That means that my 1 copper has to cancel out by being a +2. So this is copper Roman numeral 2 chloride. Then this, the prefix for 2 when we're talking about covalent prefixes, prefix for 2 is di. So this is di hydrate. So then I have ZnSO4. Zn is a transition metal, but hopefully in your regular level chemistry you memorize that it's one that has a set charge, so we do not use a Roman numeral for it. Its charge is always a positive 2. We do not have to list a Roman numeral because if it has a set charge, the Roman numeral is unnecessary and makes it wrong. So it's just zinc. And SO4, again, review your polyatomic ions, is sulfate. Prefix for 7. So our prefixes go mono, di, tri, tetra, penta, hexa, hepta. So our prefix for that is hepta. So it's heptahydrate. Then this one is asking me to go from the name to the formula. So Cu, the Roman numeral tells me my charge of Cu is positive 2. Sulfate, I just told you a minute ago, is SO4. Its charge is a negative 2. So its formula is just CuSO4 dot to show that it's chemically bonded. Pentahydrate, penta is 5. So 5H2O. So for every copper sulfate, there are 5 waters chemically attached to it in this type of hydrate. So for this step, it is going to, again, be a several step sort of problem. And so first thing we have to figure out is how much water was actually lost. And then we got to figure out our moles of the water lost. We have to find the mass of the anhydrous compound. So like what's left over after the water is driven off. Again, it's not truly just evaporating. They're chemically breaking that hydrate bond. Then it says determine the moles of the anhydrous compound left over. Find a ratio of the water to the anhydrate. Divide the moles of H2O by the moles of anhydrous compound to find the number. And then this is the number of your hydrates. If you're setting it up, it'll be in place of that X. So this one says, suppose you have a 4.13 gram sample of barium chloride hydrate, and after heating, the mass of the anhydrous barium chloride is 3.52. What is the formula for the hydrate? So this one gives me my 4.13 grams is the total compound, and the 3.52 is anhydrous, so that's what's left over. So if I go back here, to figure out my grams of water lost in this type of problem, I'm going to have to subtract those two numbers to figure out how much water was driven off, because that's the missing mass, is the amount of water that was driven off. So then once I know that value, again, I can go back here. I have to figure out my moles of my anhydrous compound and my moles of my water lost. And then I'm going to take H2O divided by my anhydrous compound, and that gives me my ratio. So let's start by subtracting these two numbers out. And so if I do 4.13 grams minus 3.52 grams, it gives me 0.61 grams, and that's actually of my water. So now I'm going to come down here, and it says that I need to convert that into moles. So again, we've seen the mass of water a few times now. So 0.61 divided by 18.016 gives me 0.034, because I only need 2 sig figs, moles of H2O. And then I already know my amount of anhydrous, so I just have to do 3.52 grams. I do have to figure out the formula for barium chloride. So barium is a positive 2. Chlorine is a negative 1. So my final formula is going to be BaCl2. Again, if you need to review naming compounds or adding formulas, you need to do that because that's a pretty common basis, and I don't reteach it. It's just something you need to review back through. It's going to do grams of BaCl2 to 1 mole of BaCl2. So then whenever I'm doing this, I'm going to take 1 barium and 2 chlorines. So barium is 137.33 for its mass, plus the mass of chlorine is 35.45 times 2. So it comes out to 208.23. So then I do 3.52 divided by 208.23. That gives me 0. Again, this one I need 3 sig figs, so 169 moles of BaCl2. So then to find my ratio, I'm going to take my moles of my water divided by moles of barium chloride to figure out the amount for my hydrate. Because what we're trying to do is we're trying to figure out N. We got to figure out how many hydrates are available. They use the letter N to represent that most of the time. And so I've got to do this math to figure that out. So then if I do 0.034 divided by I think I left off, I did. 0.0169. It comes out to a ratio of 2. It's 2.0. So then my answer would be that it is BaCl2 times 2H2O, because that's actually what I'm trying to figure out is the formula of the hydrate. This whole thing is part of the formula for the hydrate because they are chemically attached. So you can't just say 2H2O because that's not actually the chemical formula. Okay, so again, several steps, just like our combustion one. But we're thinking about this one differently because we are dealing with compounds and comparing the ratio of those compounds to each other. So then this is an example of an FRQ question where they are going to ask you to work out this problem, and you're trying to figure out what the formula is of the hydrate, but it gives you a lot of information. So it says you have a mass of an empty container, the initial mass of the sample in the container. You have the mass of the sample after first heating, after second heating, and after third heating. So in this type of lab situation, we heat things multiple times to make sure that we have driven off all of those waters. We have to break that bond, and it takes a lot of energy to break the bond. It takes to break, so we have to break that chemical bond. And so up here, we start out that the mass of the sample is 0.982, and then it goes to 0.976, and then 0.977. If it stays about the same, we're going to consider that all the water has been driven off at that point. So then here we have several steps, and this is how AP likes to do things. They like to have lots of steps that you have to answer. So it says, explain why the student can correctly conclude that the hydrate was heated it to a sufficient number of times in the experiment. And I'm just going to read this one out because there's no way I can write out this on this slide. You don't have to word things super fancy for AP. AP likes to see the answer. If you are clear and concise, they are absolutely fine with that. They don't even care if you write incomplete sentences. They just want to see that you are explaining the chemistry behind their question. So I said, as the hydrate is heated, the water is driven off. As the water is driven off, the mass will decrease. Once the mass stays the same, then the hydrate was heated a sufficient number of times. Again, you can word that in any way that you want to, but we see the proof because it started at this value and then went down and it stayed pretty much the same because we're talking about a value that's in the thousandth place. That is a very small amount of change when we're talking about that far out. And so you can word that however you need to. Then letter B asks us to use the data above to calculate the total number of moles lost of water and what's the formula of the hydrated compound. And so what we're going to have to do first is figure out how much water was actually lost in this problem. And so to do that, we are going to go back to the initial mass of the sample and the container, because at that point we know that this is the total mass of the compound with its water, because we haven't heated it, and this is also going to include the container. We're going to subtract our last heating from it. So we're going to do subtract the 23.977, because this is after all the water has been driven off, and that's going to give me my number of grams of my water, because this has water, this has no water. That's the whole point of these steps. So then I'm going to go ahead and work that part out. So I have 25.825 grams minus 23.977 grams. And that gives me 1.848. And that is my water. So then it asks for the number of moles. So then I'm going to use that number and do just a basic gram to mole conversion. Again, I'm not recalculating water because it's stuck in my head at this point, because we've used it several times in our last few problems. So then I'm going to do 1.848 divided by 18.016. And that gives me 0.1026. Then it says determine the formula for the hydrate. Well, before we can do that, I have to figure out my moles of my MgCl2. I have to figure out my moles of my anhydrous part. And so to do that, we are going to go here and subtract the empty container from it, because this is just the leftover MgCl2 at this point. This is just the container. And so if I subtract this minus that, it is going to give me just my MgCl2. So I'm going to do 23.977 grams minus 22.347 grams. And that is going to give me 1.630 grams. And then I do the same thing I did here. I'm just going to convert it over. This is MgCl2, it tells me up here. I'm going to find the mass of that. So 1 magnesium is 24.3, and then my chlorines are 35.45 times 2. That gives me 95.2. So I'm going to work that out. So 1.630 divided by 95.2. And rounded to 4 sig figs, I get 0.01712. And then based on my steps, I'm going to take this ratio divided by this ratio to figure out my N. And so I'll do that up here. I'm running out of room. So I'm going to do 0.1026 divided by 0.01712. And that gives me 5.99, which is going to round up to 6. So again, I'm not completely done because it says, what's the formula for the hydrate? So I'm going to say MgCl2 dot to show that it's chemically bonded. It's not a time symbol. Times 6H2O. This is how the AP is going to do it. They're going to ask you a question, but they don't necessarily baby step it and tell you all the steps that you have to do to get to there. We had to do a whole lot of stuff up here to be able to get to that final answer. And after we practice it enough, then we know how to get to that answer. So again, this is a more complicated method of figuring out what our empirical formula is. This is the empirical formula for a hydrate. And it does take several steps, and AP likes giving us data tables like this, and we just have to know how to use them and how to read them.